be talking about VMC, what that means, and how it applies to multi-engine aircraft. I'm Kevin Rice. I'm a CFI, II, and MEI here in Sanford, Florida with the Orlando Sanford Flying Club. Click down below for information on how to get your multi-engine rating, your MEI, or just become a pilot and get private pilot rating all the way through your ATP. So let's get started. Let's go ahead and define what VMC is. So VMC, by definition, is velocity minimum controllable.
So here the pilot is flying.
What that means is minimum controllable airspeed
Before he gets to this little one, he has to
in a multi-engine airplane with the critical engine in-out. Okay, so when we look at a definition like this, we have to really dissect it for what it's trying to tell us. What it's trying to tell us is we have to see controllable airspeed and critical engine. So, okay, that's two things that we need to figure out. And we're going to talk about that a little bit, but first we have to define the controllable airspeed and how we find that, and then we have to figure out what a critical engine is, and that's what we're here to do today. So, defining or finding VMC is up to the manufacturers of the aircraft. So I'm going to show you a little bit of an example that I like to use. So to determine VMC, the aircraft manufacturer actually uses test pilots when they create a new airplane to go out, fly test it with VMC chutes or rollover chutes. They'll actually VMC roll the aircraft, deploy a chute, somewhat safely make it back to the ground. The example I want to use is as if you were wanting to buy an airplane. So you are manufacturer A, and I'm manufacturer B. You're a really honest person. So you say you have a VMC speed of 60 knots. I'm a liar because all I want is money. So I say I have a VMC speed of 20 knots. Now, you always want a lower VMC speed because that is a lower airspeed that you can constantly maintain directional control of the airplane. It's basically the same as a stall speed. You want a really, really low stall speed as opposed to a high stall speed. So if both of us have a normal cruise of 100 knots, and our aircraft are priced the exact same, you will more than likely give me your money. However, I'm a liar. I say my VMC speed is 20 knots, when in reality, it's actually 60 knots. So I start killing a bunch of people because you think you're getting something that you're not. So people are going to about 60 knots and then VMC rolling, where they lose directional control of the aircraft, they plummet into a stall spin, unrecoverable, and they die. The FAA does not like when people kill themselves in an aircraft or pilots are unsafe. So the FAA actually levels the playing field. The way the FAA levels the playing field is something called FAR 25-149. And that determines VMC. So the FAA gives a select criteria to combat me being a liar and killing people. And that's the acronym that we're going to use today. It's going to be COMBAT. So COMBAT is what we use with 25-149 to determine how to get VMC. The C in COMBAT is critical engine, in-op, and windmilling. A windmilling engine, we already know, has the most drag effect on our airplane. So that is the what we absolutely don't want. The O is the operating engine.
And in those days, they didn't know these high altitude winds were 100 knots. So now they're flying into
At the max continuous horsepower. In the Seminole that we teach here at Orlando Sanford Flying Club, that's going to be full forward, full power. So for the M, I like to say maximum gross weight. In the actual regulation 25-149, it's the most unfavorable weight in regard to takeoff weight. That usually is our maximum gross weight that we can take off. The B in the combat's acronym is a bank of no more than 5 degrees into the operating engine. That's where the saying raise the dead comes into play. The A is an aft CG. We know that an aft CG is a little more unfavorable because everything in multi-engine flying comes down to the rudder. If we have an aft CG, we have a smaller arm to that rudder, we have less control authority over it. The T is takeoff settings. That includes our gear up, our flaps in the specified takeoff configuration, and our trim set for takeoff. And then S, the only thing the FAA helps us out with is a standard day, and we're allowed to use a test pilot. So us in our regular lives flying around, we're going to adhere to these rules and make sure we don't go below the red radial line, which is our VMC line. We're not test pilots, so let's not try to test VMC out. So this is how the FAA levels the playing field to combat me being a liar and making all this money and injuring and hurting innocent people. So again, we see this thing that says critical engine. So we need to figure out what a critical engine is. Thankfully, in our Piper Seminole here at Orlando Sanford Flying Club, we don't have a critical engine. We have counter-rotating propellers. So let's go ahead and take a second. I'm going to erase everything on the board and teach you about a critical engine. So now we're going to define critical engine because we just found out what determines VMC, but we still have this term that we're unfamiliar with, the critical engine. For critical engine, that's going to be the PAST acronym. Okay? The PAST acronym is just like single engine flying. The P stands for P factor, A for accelerated slipstream, S for spiraling slipstream, and T for torque. So let's talk about the P factor, which is prop factor. If we look at two airplanes here that you can barely see because I'm going to switch markers now, we're going to have our two engines, because again, we're flying multi-engine airplanes. And the nose is up this way, right? So we have our two airplanes and they're both going north or nose up. Let's go ahead and fail the left engine on our left airplane and our right engine on our right airplane. Now the P factor, as we already know, is producing that thrust from that descending blade as opposed to the ascending blade. So our thrust looks like that on there and like that on here. And again, this is a conventional twin. This is the most commonly found twin engine aircraft in today's general aviation world. Conventional twin means both of our engines rotate clockwise. As opposed to here at Orlando Sanford Flying Club, we have counter-rotating propellers. So our P factor right here is our thrust diagram. Everything again comes back to that arm. So my arm length from my center of gravity is further with my right engine operating than it is with my left engine operating. Again, like we mentioned earlier, everything comes back down to that rudder force. So as my P factor is trying to make me go this way on this engine and this way on that engine, my rudder has to combat that. Opposite direction, yaw. Now you just heard me say something called yaw. the first thing that happens when we lose an engine in a multi-engine aircraft is the yaw. You will always feel that pivot around that center of gravity. That's called a yaw, and P factor is responsible for it. So our rudder has to really combat this yaw. We have more coming out with the right engine operating than we do with the left. So our rudder only has so much control authority, making the left engine the critical engine. So we know that the P means P factor, which equals my yaw, which equals my left engine is the critical engine. Now let's talk about my A. My A is asymmetric thrust. So again, we're going to draw two airplanes here. And I'm going to put my two engines. 1, 2, 1, 2. In this example, I'm going to fail my left engine on my left, my right engine on the right. My accelerated slipstream, we know as our airplane flies through the air, we're producing equal lift. However, behind our engine, we're accelerating that lift because we have a big fan pushing more air over that area of the engine. So on my operating engine, I have more thrust, and this is over-exaggerated, over that wing, creating a little bit more lift. And on my other side, it's all equal. So that accelerated slipstream is creating more lift in that wing, which equals my bank. Going back to my combats acronym, we already know that we can bank no more than 5 degrees into the operating engine. So with the accelerated slipstream on my left example, that means my airplane's going to go this way. On my accelerated slipstream example for the right side, I'm going to go this way. So I have to combat this bank, again, with aileron correction and with that rudder. My bank is going to go this way, so my rudder has to combat it to the left, making my right foot my dead foot, right foot dead engine. Again, over here, I'm going to combat with my rudder. So my brown is my rudder, my black is my accelerated slipstream. So the on distance, again, because of my rudder, has less authority with my left engine being inoperative, making my left engine the critical engine. So when we look at our A, we have accelerated slipstream equals bank equals left engine critical engine. So now let's talk about my S. My S is my spiral slipstream. And let's find out what that equals. So let's go ahead and draw two new airplane examples. Again, my noses are pointing this way. So right now on both of these examples, we're looking at the airplane from behind. I'm going to go ahead and draw my propellers here. And on the same thing, here's my left, here's my right. I'm going to go ahead and fail my left, fail my right. So now for my spiraling slipstream, my left engine, which is no longer there because it's failed, is producing no slipstream, or spiraling slipstream. However, my right engine is producing all of this spiraling slipstream. My right engine on my right example is failed, so my left engine is producing spiraling slipstream. We know that we need airflow over our rudder. So as you can see in my left example, my spiraling slipstream does absolutely nothing for me. However, in my right example, with my left engine still operating, I get a little bit more airflow over that rudder to help me combat that right engine being inoperative, helping me out a little bit more, making my left engine the critical engine. Lastly, we're going to talk about torque. So our T is our torque. So we're going to go ahead and draw our airplane examples. In my left example, I'm going to fail my left engine. In my right example, I'm going to fail my right engine. So we know in our conventional twin, everything spins clockwise. Newton's law says that for every action, there's an equal and opposite reaction. So our engines that are mounted to the airplane want to go ahead and start spinning that opposite direction. In a single engine airplane that you're used to, we know that as again P factor as torque, that when we lift off the ground, we have to add all that right rudder to maintain centerline. It's the same principle in multi-engine flying. When we lift off the ground, we have a little bit more right rudder, but when we lose an engine, that torque effect is increased depending on which engine we lose. So if we lose our left engine in this example, our torque from our right engine wants to go this way, so we have to combat our rudder this way, and now we have those opposing forces really working against each other. Now, in my right example, with my left engine operating and my right engine failed, my rudder has to go this way. So instead of really fighting that rudder off, they both go in the same direction. This engine, with that torque effect, is actually helping me as opposed to hurting me, making again my left engine the critical engine. Ultimately, we know a critical engine is the engine that most negatively affects flight characteristics and performance and handling of the aircraft. After talking about all of these examples, we know in a United States-made conventional twin, our left engine will usually always be our critical engine. So after talking today, we understand that VMC is velocity minimum controllable with our critical engine inoperative, that we can still maintain directional control. Anything below VMC specified by 25.149 of the FAR means we're entering some danger zone and becoming test pilots. If there's anything you take away from today's lesson, that is, do not become a test pilot. We want to go fast, we want to get places and see cool things, and us spiraling towards the ground is not something we want to see. So in conclusion, on our airspeed indicator, VMC, which is depicted by a red radial line, is the minimum controllable airspeed, or the airspeed that when we get to it, we are still able to maintain directional control of the aircraft with our critical engine in a conventional twin. That means our left engine inoperative. So I really hope you took away our VMC demonstration with that little story time about you being an aircraft manufacturer, me being a horrible person and lying, and understanding that the FAA combats that playing field when it comes to certifying new aircraft with FAR 25-149. This was just my little story time, and this does not cover going out in the air with a CFI or reading the FAR 25-149, where you can find more specifics on certifying VMC. However, if you do want to get a multi-engine rating, we are available here, and you can go down in the description below for my contact information or for any information on the Flying Club here at Sanford, Florida. I really want to say thank you for watching our VMC demonstration. I hope you understand VMC, critical engine, and I look forward to helping you guys achieve your goals when it comes to multi-engine flying. Have a great one. Don't forget to like and subscribe.